Hey everybody, so I'm going to attempt to go quickly through all of the review problems in our packet that was handed out in class today. We did the majority of them, so if you just need a few quick tips, or you want to see the answers to the last few, please scroll to the end of the video. So I'm going to go back and redo everything we did in class. All right, so starting with the main ideas from section P2, we had slope and writing equations of lines, and so you need to know that the slopes of parallel lines are congruent and the slopes of perpendicular lines are negative reciprocals. So in our first question, it says determine if the lines are parallel, perpendicular, or neither, and how do you know? So we're going to know by checking out the slopes. So in that first equation, we're going to rewrite it first as 3y equals negative 2x plus 5, and then take and divide everything by 3, and we get y equals negative 2/3 x plus 5/3. So that gives us a slope of negative 2/3 for this line. In the second case, our equation is written in point slope form, and this number right here, 3/2, is our slope. If we compare the two slopes, obviously they're not the same, so the lines cannot be parallel to each other. And now check and see if the slopes are negative reciprocals. They are. 2/3, the reciprocal would be 3/2. The first slope is negative, second slope is positive, so the lines are perpendicular. I'm sorry about my writing. So we're going to say in writing the lines are perpendicular because the slopes are negative reciprocals. If you're not sure if your two numbers are negative reciprocals, multiply them together. If we take 3/2 times negative 2/3, we get negative 6 over positive 6, which reduces to negative 1. So that proves that they're negative reciprocals. Negative reciprocals always multiply to give us negative 1. Okay, number 2 is actually a homework question, and we talked about it in class, but just to go over it one more time. It says find the value of t such that all three of these points are collinear. So we're going to check out the slopes, because the slopes between the first 2 points and the last 2 points need to be equal in order for all 3 points to be on the same line. So our first slope will be t minus 5 divided by 0 minus a negative 2. And that's going to simplify into t minus 5 over 2. The second slope, I can set it up as t minus 1 over 0 minus 1, or t minus 1 over negative 1. Okay, so let's set these slopes equal to each other, and then that will give us a proportion that we will then solve for t. So cross multiply, we have negative 1 times t minus 5 is equal to 2 times t minus 1. So you get negative t plus 5 equals 2t minus 2. So keep going. We end up with 7 on this side. Of course I wrote 5, so let's erase that. So I have 7 is equal to 3t. And take and divide by 3, we get t is equal to 7/3. So that's it. The value of t must be 7/3. And number 3, it says write an equation for the line that passes through the point negative 4, 7, and also through the point 2, negative 5. First thing we need to do is find the slope. So I can set it up as the change in y, or 7 minus that negative 5, which will become 12. Because it's 7 plus 5, and then divide it by negative 4 minus 2, which is negative 6. So that's nice. Our slope is negative 2. Now you can either use point slope form or y equals mx plus b form, slope-intercept form, to come up with the y-intercept. I'm going to use point slope form. So I would do y minus a y value, which is 7, equals our slope of negative 2 times x minus negative 4. Now, that's going to turn into addition, so why don't we just put that in there. So we have, sorry about that, we have y minus 7 crazy writing. Y minus 7 equals negative 2x minus 8. So y is equal to negative 2x minus 1 after I get the like terms together. Okay, and number 4, it says write the equation of the line through the point 6, negative 4. So we've got x value of 6, y value of negative 4. And it's going to be parallel to 3/4 x plus 3. So our slope needs to be 3/4. And we can use point slope form to come up with that equation. So do y minus the y value of our point, which is negative 4, equals 3/4 times x minus 6. So you have y plus 4 is equal to 3/4 times x, and this will be equal to negative 9 over 2. I multiplied 3/4 by negative 6 and got negative 18 over 4, and then I reduced it to negative 9 over 2. Okay, we need to subtract 4 from both sides, so I have y equals 3/4 x minus 9 over 2 minus 4. And we need to simplify that by getting a common denominator. So we have y equals 3/4 x minus 9 over 2 minus 8 over 2. So final answer for part A would be y equals 3/4 x minus 17 over 2. Okay, leave it as an improper fraction, okay? In the second case, part B, we want to write the equation of the line perpendicular to 2/3 x minus 2, so our slope needs to be negative 3 over 2. And again, use point slope form. So we know it's going to be y minus a negative 4, so it'll change into y plus 4, and that's going to be equal to negative 3/2 times x minus 6. Now, we have a little bit of a break here with dealing with this fraction. We will have negative 3/2 x, but when I take negative 3/2 times negative 6, first it turns into a positive, and it's just going to be positive 9. So much easier to find that y-intercept. So you get y equals negative 3/2 x plus 5. In question number 5, it says find all intercepts for the equation y equals x cubed minus 3x squared minus 4x plus 12. Then sketch a graph of the function. Determine the type of symmetry, if any. So first, I'm going to start with the y-intercept because that's easy. The y-intercept happens when x equals 0. So when x equals 0, the y value will simply be 12. Okay, so far in our graph, I know we're going to be up here at positive 12 for the y-intercept. All right, so if we're doing it on a piece of graph paper, you want to change the scale and do all that good stuff. All right, with the x-intercepts, we're going to set this equal to 0. We want to know when y equals 0, what's going on with x terms. And I see that it is, sorry, trying to edit a little bit. This should be a 3. We have 4 terms, and we have x cubed in there. We want to factor this by grouping. Again, that's because there are 4 terms. All right, let's write the next line a little bit neater. From these first 2 terms, I would factor out x squared, and that leaves me with x minus 3. From these 2 terms, factor out negative 4, and again, it leaves you with x minus 3. You have to get this set of parentheses to be the same. Okay, the rule of factoring by grouping is you take out that common factor, x minus 3, and then in the parentheses will go whatever's left over, which is the x squared minus 4. Keep going, factor one more time. The x squared minus 4 factors into x plus 2 times x minus 2. So that leaves us with x-intercepts at positive 3, 0, negative 2, 0, and positive 2, 0. Okay, so it's going to look kind of funky because these 2 intercepts at positive 2 and positive 3 are so close together, and then we have one over here at negative 2. Okay, also consider the end behavior. That leading coefficient is positive, and it's an odd degree, so it's going to go downward to the left and upward to the right. So I would probably start from the upper right-hand corner, like in quadrant 1, come down through, up through the x-axis of positive 2, all the way up to that y-axis, and then back down to that final intercept. Okay, so we're just sketching. All right, this particular equation has no symmetry. On the test, you'd be asked to show your work. So if we did that with the y-axis, test for symmetry, we replace x with negative x. Okay, for test for symmetry, remember that a quick thing to look for are even exponents. If you have even exponents on x, then you really want to do a quick test for symmetry with respect to the y-axis. Symmetry with respect to the y-axis means you're taking each x value and replacing it with negative x and seeing if you get back to the original equation. So in this one, you're going to see that it works. So you have negative x in parentheses quantity squared, y cubed equals 5. And that does simplify to x squared, y cubed equals 5. Because you need to show that it's the same as the original. Okay. In part B, I notice odd exponents on x, so it's not going to have y-axis symmetry, but I know an even exponent on my only y term, so I'm thinking that this is going to have symmetry with respect to the x-axis. So that means that we want to keep the x's the same, but this time replace y with negative y and simplify. So this becomes 2x cubed minus x equals y squared plus 5. We're back to the original, so it is symmetric with respect to the x-axis. All of our equations on the test will only have one type of symmetry. We're not working with circles or ellipses or hyperbolas, so if you can make an educated guess as to which type of symmetry it is, and you do the test and the answer is yes, then you're done. You don't have to do any other symmetry tests. If the answer is no, you have to keep going, okay, until it's no for all three. Okay, number 7 is just an exercise in algebra. It says if f of x equals x squared plus 3x, find f of x plus h minus 2 times f of x. Okay, so to do f of x plus h, you're going to replace each of those x's with x plus h. So that is going to give us x plus h quantity squared plus 3 times x plus h. Now from that we have to subtract 2 times f of x, so it'll be minus 2 times x squared plus 3x. Alright, x plus h quantity squared gives us x squared plus 2xh plus h squared. 3 times the quantity of x plus h gives us 3x plus 3h. And then we have to subtract, or we have to distribute that negative, so we have to subtract 2x squared, and then take negative 2 times positive 3x, so you get negative 3x. Alright, combine your like terms. I have x squared and negative 2x squared, so that's a negative 1x squared. 2xh doesn't have a like term, so bring it down. H squared doesn't have a like term, so bring that down. 3x, that should be minus 6x on the end, excuse me. Okay, so 3x right here and negative 6x will give us negative 3x. I wrote 6, so let's erase that. And again, I apologize for my mistake there. And then we have this 3h. It doesn't have any like terms, so you can bring that down. It doesn't matter to me what order the terms are written in. When we get to exercises like this, later in calculus, we'll talk about what order they should be in. Okay, for number 8, we're going to take the function f of x equals x squared minus 2x, and we're going to find f of negative 2. So we're going to be doing 2 substitutions. So first start on the inside and do f of negative 2, which will give you negative 2 squared minus 2 times negative 2, which yields 4 plus 4, which is 8. Okay, so f of negative 2 now becomes f of 8, because we've figured out, we evaluated f of negative 2, Our output was 8, so now we're going to go back to our function f of x, and this time we're plugging in 8 everywhere we see x. So we're going to do 8 squared minus 2 times 8. So you get 64 minus 16, which gives us 48. Okay, and number 9, we have a piecewise function. So we're going to graph it and then identify the range. Okay, so the first part of this piecewise function is a line. And so if we go to where x equals -1, if I plug in -1, imagine you're making a table. If I plug in -1 for x, my output will be -3, because -1 times 2 is -2, minus 1 gives you -3. All right, if I plug in -2, we'll get a sense of which direction this line is going in. When x equals -2, y actually equals -5. So -2, we're at -5. So this line would look something like this. I know it's a really rough sketch. Okay, so that's our first piece. The second piece, x squared plus 3 is a quadratic, obviously. It's going to be a parabola when we graph it. So it might be useful to make a quick little table of values to get a sense of that. It is a parabola that's been moved up 3 on the y-axis, but we actually want to start our table at -1 and then see what happens at 0, 1, and +2. I'm stopping at that upper limit there. When x equals -1, -1 squared is 1 plus 3 is 4. So -1, we're up a +4, but we need to put an open circle because x does not actually equal -1 for this piece of the function. When x equals 0, y is going to equal 3, so we'll be here. When x equals 1, we're going back up to +4, so that'll give you the shape of the parabola. And when x equals 2, we'll be at +7. And it's going to end there. Okay, so it doesn't have an arrow on the end, it doesn't continue on forever. All right, the last piece is actually going to be a horizontal line at y equals 4. So we're going to go to where x equals 2. We go up to 4, so 1, 2, 3, 4. We're going to have an open circle, and then after that, every y value is 4. When x equals 3, y equals 4. When x equals 4, y equals 4. Okay, so we want to find the range. So for the range, we know that we're going to start at the bottom from -infinity, and then we're coming up on the y-axis, and we're going to come up to -3. Then we're going to bracket it because y can equal -3. When x equals -1, y was equal to -3 for our first piece. So for the second part of our range, we'll say that this first piece is in union with the second part, and the second part starts up here where y is equal to +3, so we need a bracket and then +3, and then it's going all the way up here to where y is equal to +7, and it stops there. So it's the interval from 3 to +7, including the +7, because that's the maximum for our parabola, because the upper limit on the x values for the parabola is +2, and when x equals +2, y has a value of +7. There's a point there and not an arrow, so that's why it does not go off to +infinity. Okay, and number 10, we have if f of x equals x to the 4th minus 2x squared minus 3, and g of x equals 3 minus x, we want to find the composition h of x that is equal to f of g of x. And we have to state its domain. Okay, so the first thing we need to do is actually find the domain of each of these two functions. Now, this first function, f of x, if you were to graph it, just thinking about the general shape of it, I'm not going to get into finding the intercepts or anything, but it's going to be one of those graphs, a 4th degree polynomial, so it could have as many as 4 x-intercepts. And the end behavior is the same because it's x to the 4th power. So left and right both go up to +infinity. but the domain for that function is just negative infinity to positive infinity. There's no point at which it's undefined, so no restrictions on x. In the second case, that g of x equals the square root of 3 minus x, you can tell pretty quickly that the x-intercept is at positive 3. I don't know why those are so big. So when I put positive 3 into my equation, I get 0 out. So there's definitely a point at 3, 0. If it helps, make a table. Okay, so at positive 3, we end up with 0. I know I can't go any bigger than positive 3, because if I put in positive 4, then I have 3 minus 4, which is negative 1, and now we're looking at the square root of negative 1, which would be imaginary. So instead of going greater than 3, we actually want to go less than 3. So see what happens at 2, at 1, at 0, even see what happens at, say, I don't know, you can do like negative 1 as well. So when x is equal to positive 2, y would be equal to 1, because 3 minus 2 is 1, the square root of 1 is 1. So positive 2 for x, we're at positive 1. When x equals 1, it would be the square root of 2, or like 1.414. If you could put 0 in there, you'd get the square root of 3. If I put negative 1 in there, I would end up with a y value of positive 2. So all that just goes to show that your graph is going to be the square root function going off to the left. Okay, so the domain in this particular case for this inside function is just all real numbers from negative infinity stopping at positive 3, but it does include positive 3. It's defined at x equals positive 3, but that's the maximum value for x. Beyond positive 3, it's undefined. Okay, so keep this in mind because this is the domain of the inside function of our composition. So any restrictions that apply to the inside function are going to apply to our end result of the composition. So figuring out h of x, we're going to do the composition. So replace g of x, or plug g of x in here. So we have the square root of 3 minus x. And then we're going to plug that into our function f of x. So you actually have the square root of 3 minus x raised to the 4th minus 2 times the square root of 3 minus x squared minus 3. Now remember what you've learned about rational exponents. I could rewrite this as 3 minus x raised to the 4 over 2. Because it's the exponent divided by the root. Square root is 2. And that's going to simplify to 3 minus x squared. Okay, in the second case, we're just going to have 3 minus x, because that would be 2 divided by 2. We take the exponent divided by the root, so that's equivalent to 1. So we don't need an exponent there. And then we're subtracting 3 on the end. So I'm going to expand that part. So negative 2 times 3 is negative 6. Negative 2 times negative x is positive 2x minus 3. Okay, expanding this, remember we have to write it out twice. Use FOIL, but hopefully you're at the point you can do that in your head. You've got 9 minus 6x plus x squared minus 6 plus 2x minus 3. Push that up a little bit. Combine your like terms. We've got x squared, and then we have negative 6x plus 2x. That's a negative 4x. And then we have 9 minus 6, which is 3, and then minus 3. So this is it. This is our function h of x, because all those constants would combine to give us 0. Okay, we know that this is quadratic. So its graph would be a parabola, so its domain would be from negative infinity to positive infinity. But remember that this quadratic function was formed by doing the composition of two functions. So this domain doesn't apply. We have to go with the most restricted domain. Go back to the original inside function g of x, and recall that its domain went from negative infinity to positive 3. So this is our final answer for the domain for this composition. Okay, we talked about this one briefly at the very end of class for us to find the domain and range for y equals negative 2 times the square root of x plus 4 plus 3. So if you go back to thinking about just the square root of x, we should know that this parent function, the most basic of the square root functions, looks like this. So obviously this new one is being transformed. Okay, so the positive 3 is going to cause the function to go up 3. The x plus 4 inside the radical is going to make it go to the left 4. The 2 is going to change like the height of the graph. It's going to be 2 times taller. So if this were, if I graphed y equals 2 square root of x here, it would look something like that. And then finally, the negative is going to reflect the function over the x-axis. Like if we were talking about a parabola, we would say like it opens down, okay? So the negative would cause it to go that way. Okay, so let's get a visual on this. So I'm going to start by doing the horizontal and vertical transformations. So I want to go to the left 4, and then up 3, and I'll put that point here. Okay, so we've got negative 4, and when I put negative 4 in here, if I'm thinking about my table, so negative 4 is going to yield positive 3, so you can test it out. Okay, you might want to see what happens at negative 3. When I plug in negative 3, I end up with positive 1. If I plug in negative 2, I'm going to get negative 2 square root of 2 plus 3, so not the best point or not the easiest point to graph. So probably another good point to use to get an understanding of the graph is to see what happens at 0. Because I can do 0 plus 4, get the square root of 4. So it's negative 2 times 2, which is negative 4, plus 3 gives me negative 1. So at 0, we're at negative 1. So in other words, we're looking at the y-intercept. So this graph is going to go like this. It stops here. Because I can't use x equals negative 5, because when I do that, it makes this part undefined, or it makes it imaginary. Okay. So in thinking about the domain, we're not going to start from negative infinity because our graph doesn't exist to the left of negative 4 on the x-axis. So we're not using anything smaller than negative 4 for x. So we're going to have a closed off bracket at negative 4. And then our graph does use everything to the right and it continues on. So it's going to go off to positive infinity. Okay. Now, as far as the range goes, so the range, very often we find the range by, oops, sorry, that should be a parenthesis here. Okay, so parenthesis on that side. The range, we want to think about all the values of y that are possible to use. And if you notice here that this point is the top, the highest point on our graph. So that's the maximum y value, okay? And this graph continues on down in the negative direction for y. So if we think about reading it from the bottom up, we would start at negative infinity. And then we're coming up to a maximum value of y of positive 3. And y can equal negative 3, so we're going to use a bracket there. Okay, so domain is negative 4 to infinity. Range is negative infinity to positive 3. Okay, just really quick, the graph of the sine function. We know the general shape of it like that. Well, this is 2 times the sine function, so the amplitude is going to be positive 2 to negative 2. Okay, so it's going to look something like this. A height of positive 2 down to negative 2. And we know that the sine function just continues on in both directions to positive and negative infinity. So the domain will just simply be negative infinity to positive infinity. The range, though, has a minimum and maximum. And the minimum value is going to be negative 2, and it can equal negative 2. For instance, when x is equal to 3 pi over 2 in this equation, then the y value would be negative 2. And the maximum height is going to happen at pi over 2, or 90 degrees, and it would be equal to positive 2. So brackets around both of those. For part B, we're asked to find the domain only. You really need to just focus on the denominator. Okay, so in the denominator, x squared plus 2x minus 15, we're going to set it equal to 0 and then factor it. So you get x plus 5 times x minus 3. So x cannot equal 5 or positive 3. So when we go to write the domain of this function, we're going to start with negative infinity. And we'll go to, this should say negative 5 up here. So x cannot equal negative 5. And this will be in union with the set from negative 5 to positive 3. And then this is in union with the set from 3 to positive infinity. Okay, you may notice that in your function you have 5x times x minus 3 divided by x plus 5 times x minus 3. And in here the x minus 3's would divide out. That means we've got a hole in the function. It means we have a place where the graph is undefined. So that's why we have to break it up into 3 sections for the domain. Finally, for part C, we have to find the domain only for this function. So x cannot equal 0. So with this particular function, the domain would go from negative infinity to 0 with parentheses, because x can definitely not equal 0 because it's undefined at x equals 0. And that's in union with the set from 0 to positive infinity. Okay. If it helps, then sketch a graph. So for example, when x equals 1, y equals 2. When x equals 2, y equals 1. When x equals 3, y equals 2/3. This graph is coming in like this. And it's doing that on this side as well. So when figuring out the domain, you're coming in from negative infinity. You're approaching x equals 0, but x cannot equal 0, hence the parenthesis. And then on the other side, we're starting at 0 because we can get infinitely close to x equals 0, so really teeny tiny, but then x just keeps getting larger and larger.